All right, it says warm up, evaluate, and simplify. The limit is x goes to 2 pi thirds of tangent of x. So if you use direct substitution, you get tangent of 2 pi thirds. And if this were a free response, is it defined there? Could you leave it like that? Yep. Yeah, you can. It is defined. But I asked you to simplify, so I'm trying to prepare you for multiple choice. What is tangent of 2 pi thirds? It's negative, right? Because it's in quadrant 2, negative, positive, and it is square root of 3. Yeah, it's going to be negative 1/2 over, no, negative square root of 3/2 over 1/2, and then the 1/2, the 2's divide out. So we've got to know the unit circle. Negative square root of 3. Just for a multiple choice question, positive square root of 3 would be an answer. Plus or minus square root of 3/3 would be an answer. And maybe like 48.2. Just to make something up. Hopefully no one would answer that. Okay, so we are going to finish the notes today. We got through example 10C yesterday. There's one more type of discontinuity you're going to be responsible for, and then there's a cool one that I'll introduce you to, and then we'll just kind of close and summarize, and that'll be it. So the example 10C, remember yesterday we were approaching E, and the graph of, I'll write it up here, we didn't write it. Natural log of x over 2 is the same as 1/2 times the natural log of x. So what would the 1/2 do to any function when it's in front? Just to review transformations. Dilates it. It's nice and generic. How? Vertically or horizontally? Vertically. Would it be a vertical stretch or a compression by a factor of 2? Compression. It's half as tall. So that doesn't really affect the overall shape. The natural log of x is one of those parent functions that you might need to review if you're not familiar with it. It looks like that, and it passes through the point 1, 0. Now the natural log of x then passes through the point e1, e squared 2, e cubed 3, but this is like 1/2 in front. So there's what the graph looks like. If I were to change this question here, or let's just add on another one, instead of we were approaching e, what if I were approaching 0 from the right-hand side? Yeah, that one's interesting. If you hop on the graph to the right of 0 and you start heading back towards 0 from the right, this is going to go down, 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 forever and ever and ever and ever and ever more. So the limit would be negative infinity, and that's the way that we want to. Well, this is the way I want you to do it. When you say that the limit is negative infinity, you are saying two things. The very first thing you're saying is DNE, because infinity or negative infinity, neither one of those are limits. Right? If I said y'all had unlimited negative potential, that means there's no limit to how low or bad y'all could be, right? There's no limit, right? Y'all could be like the dregs of society are here, and y'all go way below those people. Unlimited possibility for negative behavior. But you're also then saying why it doesn't exist. You're saying why? Because it decreases without bound. Okay? So that is acceptable on a free response to put DNE, but it certainly wouldn't be a multiple choice answer choice, okay? Now what if I flip that around and say the limit as x goes to 0 from the left-hand side on this function? Yeah, now that one has to be does not exist because there's no graph to the left of 0 for you to even jump on and start approaching 0. So this is DNE. Now the first one could be DNE also, but the reason that DNE is so good if you're not sure for a limit is because it encompasses a whole slew of reasons why some limit can fail to exist. Okay? But negative infinity implies that as you approach a specific number, in this case 0, your y values are going down forever. That's because there's a what graphical feature there? A vertical asymptote. Yeah. So let's go ahead and define the last discontinuity, which is a vertical asymptote. Okay? The formal name for a vertical asymptote is a non-removable infinite discontinuity. Now I drew a little picture over here of some random function. The natural log of x only lives on one side of its vertical asymptote. This is a function that lives on both sides of the vertical asymptote. But the reason it's called non-removable is because if I gave you a little manhole cover like that, you could not take that manhole cover and put it down anywhere on that vertical asymptote and make those two graphs connect at all. Okay? So this one goes down on the left and up on the right. There are functions that go up on both sides. And what's interesting is as they go up forever and ever and ever, they're also getting closer and closer and closer and closer to each other they're never going to touch, even then you still can't put a dot way up there and make those two things stop going up and turn in toward each other. Physically, when you draw it, it's going to happen very fast. Okay, you can't draw things infinitely close but infinitely far away at the same time. So your lines, when you draw them, may merge. Okay, so that's why it's infinite, or that's why it's removable. Why do you think it's called an infinite discontinuity? Because what? What goes to infinite? The y values, the function values, yeah. The y values or the function values are going to infinity, increasing without bound, or they're going to negative infinity, decreasing without bound. So a vertical asymptote is fine. I'll abbreviate it VA, but realize that it's a non-removable infinite discontinuity. It interrupts the graph. Okay, so now we can define an infinite discontinuity in terms of the limit, because we can define continuity in terms of a limit, a hole in terms of a limit, a jump in terms of a limit, and now a VA. So if there's a function, f of x, at some x value, call it c, so it's a specific value of x, then if any one of these four things happen, and at most two can happen, but if any one of the four happen, you're going to have a vertical asymptote at x equals c. If you approach from the right and it increases without bound, or approaching from the right decreases without bound. It could be one of those, but not both. Or from the left, it goes to positive infinity, or from the left, it goes to negative infinity. Those can have only one of those two happening. So you can have two sides, but as we saw with the natural log, it only has to happen on one side. So if anything forces, essentially, your y values to some kind of infinity at a specific location on the number line, then there's going to be a vertical asymptote at x equals that number. And it is an equation of a line, so make sure that you have x equals. Okay, so example 11, your knowledge of parent functions is going to help you answer these questions. It says to evaluate each of the following. PS, don't use a calculator if you don't have to. PSS, you don't have to. Okay, sweet. So we got h of x is equal to the natural log of x. Again, I'll sketch it very quickly. It is a parent function. You need to know what it looks like. This one passes still through the point 1, 0, but now it passes through the point e comma 1, and e squared comma 2, e cubed comma 3, so on and so forth. Its domain is everything greater than 0, but notice that it has negative values between 0 and 1, and then positive values to the right of that. Okay, sweet. So what is h of 0? Well, it's the natural log of 0, which does not exist, right? It does not exist. Okay, so you can't just leave it as a natural log of 0. Hey, Phipps. So now, what would be the limit as we approach 0 from the left-hand side? That's d and e, okay? And that's d and e for a different reason than because it increases or decreases that bound. What would be the limit from the right? This is kind of anticlimactic after we went up there, but negative infinity. Yep. Now, negative infinity, remember, is the preferred answer. On a multiple choice, when they ask you for a one-sided limit at a vertical asymptote, d and e or non-existent will not be an answer choice. Then what can we say about the general limit if from the left it's d and e and from the right it's a different kind of d and e? You have to say d and e, right. The only time you can say anything about the general limit, even if it doesn't exist, is if it's uniform behavior on both sides, whether they're approaching the same finite number or the same type of infinity. Otherwise, you have to say d and e. All right, so that one was pretty easy. 1 over x minus 3. What is f of 3? Well, when you plug in, you get 1 over 0. And remember, 1 over 0 implies vertical asymptote, but really it implies plus or minus infinity. That's what a vertical asymptote is. It forces the y values up or down to plus or minus infinity. So that's kind of interesting right there. 1 over 0 and infinity are reciprocals of each other. What's the reciprocal of infinity? 0. What's the reciprocal of 0? Infinity. And we mean that from a limit perspective. The reciprocal of a number that's approaching 0 is a number that's approaching hugely, infinitely large values. And then the reciprocal of a huge value that gets bigger and bigger is one that gets smaller and smaller approaching 0. So for the most part, 0 and infinity are reciprocals. But f of 3 is d and e. But because we know there's a vertical asymptote there now, direct substitution told us there was a vertical asymptote, you know then that for b and c, these are the two one-sided limits on either side of infinity. You know they're going to be some type of infinity, for sure. So if this were a multiple choice question, you could focus in on having a 50-50 shot, right? It's either plus or minus infinity. But we want better than 50-50 shot. So if you don't remember the parent function and you don't remember how to do transformations, how can you determine the sign of the type of infinity? Plug in numbers. Very good. Plug in numbers. Excellent. If you pick a number, since we're approaching 3 from the left, what's the number to the left of 3? 2. How about closer? 2.9. If you pick something really close to the left, like 2.9, a tenth away, because asymptotes are so powerful, you'd have to think, okay, just a tenth unit to the left, it's already well on its way towards the type of infinity it's going to be heading towards forever. So 2.9 would work. So just to the left, if you plug in a 2.9, what sign do you get? You get negative. 2.9 minus 3 is negative. 1 over a negative is a negative. So it's that easy. That's all you have to do to get the sign of the infinity. And what would be the limit from the right of 3? Well, to the right of 3, you could pick like 3.1. Plug it in here. 3.1 minus 3 is positive. 1 over positive is positive. So you can just leave it as infinity. You don't have to put plus in front of it. No, not at all. Just kind of, no, you don't really have to justify when you're evaluating a limit. You'll see in 1.4 that some of them require a little bit more work, but for a vertical asymptote, you're kind of expected to know it's a vertical asymptote, and you don't have to show how you're coming up with the sign. Good question. On part D, what can be said about the general limit as we approach 3 then? Very good. It has to be D and E. Those are different sides of infinity, so D and E is actually acceptable on a free response for all 4 of these answers. B and C on a multiple choice, and even on a free response, it's preferred to put those. But because it's not the uniform, it's not the same type of infinity on both sides, D and E is what you have to put for D. Now, you could also realize that the parent function is 1 over x. Remember, 1 over x looks like this. It's your reciprocal function. It lives in quadrants 1 and 3. That's 1 over x. And what does minus 3 do to any graph? Shifts it to the right 3. Good. So now the vertical asymptote right here is at 3. And once you kind of either draw the graph, if it's a parent function, or you just envision it in your head, now you can answer those vertical asymptote limit questions very, very easily. But you don't have to. Just pick a number. Know it's infinity. Pick a number just to the left or right to get the sign. All right, Roman numeral 3, 1 over x plus 2 quantity squared. It's asking us to evaluate g of negative 2. So what do you get when you plug in a negative 2? 0 where? In the bottom. You don't get 0 for an answer. You get 1 over 0, which again means there's a vertical asymptote on the graph, which means the y values are going to be plus or minus infinity. Okay? So g of negative 2 is d and e. That's always d and e. There is no dot on the vertical asymptote for this single function. But you now know as we approach that value from either side, we're going to be approaching some type of infinity. So you can throw that in there and then just come back and work on the sign. If we want to approach negative 2 from the left, what's the number that's just to the left of negative 2? Negative 2.1. Yeah, not negative 1.9. That's to the right. When you're in negative land, it's all backwards. So negative 2.1 plus 2 is a negative number, but then you're doing what? Squaring it. So it's positive. So it's actually positive on both of them. Even if you pick like negative 1.9, you're going to get a positive squared. Again, you don't have to put plus signs for positive. But it is plus on both sides. What then can be said about the general limit? Yeah, we can say positive infinity now. And when you say that the general limit as x approaches a finite x value is positive infinity, you're saying 3 things really. You're saying that the limit doesn't exist, but you're also saying that it increases without bound on the left side, and it increases without bound on the other side. I forgot what I said. Okay, on the left and right side. Excellent. This is a transformation, though, of a function you should know. It's a transformation of what I call the volcano graph. Looks like that. There's vertical asymptote here, horizontal there. This is 1 over x squared. And at some point, lava spews over the side. Okay. And then the plus 2 does what to this graph? Left 2. So if you do that, you see it goes up on both sides. So if you can envision it faster than like picking and plugging, that's fine. So on Roman numeral 4, you got a secant of x, and you got 4 questions. Go ahead and answer those yourself. And then you can imagine the Jeopardy song playing in the background probably 4 times. I'll give you 2 minutes. Mm-hmm. Sweet. You did it without graphing it. That's good. Let's see how you did. Secant of x is a trig function, but we're looking at the graph of that trig function. And if you remember how we sketched the graph of secant last year, secant is the reciprocal of which trig function? Cosine. So we drew chala, and then the axis points became vertical asymptotes. The highs flipped up and the lows flipped down. You don't really have to sketch it, even if it's a trig function. I'll show you how. First of all, plug in k of pi halves is secant of pi halves. And could you stop there on a free response and get credit? No. Yeah, good one. Love your sense of humor. Yeah, why can we not stop there? It looks like it's a numeric answer, but it's not because it doesn't exist. What is cosine of pi halves? 0. And what's the reciprocal of 0? Infinity, plus or minus infinity. So this one is dne. For the function value, it's always dne. You don't put like positive or negative infinity for a function value. Function value, if you get a 0 in the denominator, always dne, because the function is saying where can you stand at that x value, and you can't, okay?
Could you put negative infinity? Would that be wrong?
Yes, it would be wrong. For the function value, it would be wrong.
Yeah, but not negative infinity.
No, that would be wrong.
I mean, like, if you put negative
Negative dne, we would probably have to take that to the president of College Board and get their interpretation on it. And then it gets kicked to the NFL, and then the Players Union gets involved, and you don't want to get suspended for 6 games. So, no, just don't do that. Ezekiel Elliott, okay. But now that we know that pi halves is a vertical asymptote, how do we know it's a vertical asymptote? Because cosine of pi halves was 0, and the reciprocal of 0 is 1 over 0, which is VA, which means plus or minus infinity. We know that the answer to each of these one-sided limits is some type of infinity. So how can we figure out if it's plus or minus if we're approaching from the left side of pi halves and we don't have the graph? How'd you do it? Because you did it. Did you any, mini, miny, moe it?
I didn't grab it, but I knew it graphed it.
Oh, okay. Well, that's good too. Yeah. You can think about the unit circle, actually. Here's a 0, and here's 90 degrees. So right in here is the first quadrant, right? So here's pi halves. If we're approaching from the left of pi halves, we're approaching from the first quadrant. So if you just move just into the first quadrant, to the right of 90 degrees, all of the trig functions in quadrant 1, which is where you're at, are what sign? Positive. There you go. You don't even have to pick like pi thirds. Secant of pi thirds is positive. Secant is positive everywhere in quadrant 1, so it's positive infinity. And then if you're approaching pi halves from just to the right of pi halves, just to the right of pi halves puts you in which quadrant? Quadrant 2, where secant is what sign? Like here's 0, here's pi halves. Yeah, so here would be in quadrant 1, like at pi thirds. What's secant of pi thirds? Positive, who cares? And if you're just to the right of 90 degrees, like at 2 pi thirds, what is secant of 2 pi thirds? Negative, who cares? Right. Secant is negative everywhere in quadrant 2 and positive in quadrant 1. So when you're coming in from the right of pi halves, you're coming in from an angle that's smaller. And when you're coming in from the right side of it, it's in quadrant 2 where it's negative. Okay? So you can do it that way. And then what could be said about the general limit? It does not exist. Does everyone understand how I got the signs on these? Yeah? You can always do that if it's because they're going to be undefined at the quadrantal angles. So you can just kind of, like if it were pi, you can like float up above pi into quadrant 2 and see what the trig function sign is there, or float down right below pi in quadrant 3 and see what the sign. So it goes back to knowing the definition of the trig functions in terms of x, y, and r. Do we need to write that down? Do we need to review? Quadrants, yeah. Yeah, because when I rotate up here, here's pi halves. So this is how you can do it without looking at the graph. So if you're approaching from the, when you approach from the left of pi halves, this is why you might be confused. On the unit circle, left of pi halves is quadrant 2. But when we say left of pi halves, we mean from an angle that is just smaller than pi halves. So it puts us in quadrant 1. Maybe that's where the confusion was. If we do it on the unit circle, we can't physically move left because that makes the angles bigger. There you go. Okay. All right, because I saw some people go, I'm not confused. I'm like, pre-cal. Okay. Because we're not looking at the function on a number line. We're just rotating. Smaller angles are actually, when we approach from the left, we have to go from the right on the unit circle and vice versa. Okay. Does that make sense? Okay. That makes sense now. Good. If something doesn't make sense, you don't have to murmur it. Just say, whoa, wait, hang on. What are you talking about? And we'll get to the bottom of it. Okay, good. So that's a vertical asymptote. Another type of discontinuity. You know there's a vertical asymptote. How? Direct substitution gives what? Non-zero over 0. Good. And then for the one-sided limits, you need to commit to plus or minus infinity if the graph exists there. Natural log of x, of course, only lives on one side, as do some others. Now, there's one last type of discontinuity. It's not on the AP exam, but I think it's kind of cool. It's called the oscillating discontinuity, and we'll analyze it here through this function. F of x equals sine of 1 over x. What does it mean to oscillate? Yeah, to kind of go back and forth between. Like, what governor just converted from Democrat to Republican? Jim Justice. Yeah, from West Virginia, okay? And like next week, he's going to go back to the Democrats, right? He oscillates or vacillates in between conservative, liberal, alt-right, alt-left, alt-right, okay. We want to analyze this function in the vicinity of 0. Okay, well, how are we going to do that without a calculator or the graph? Calculator? Without a calculator or a graph, we'll do it with a calculator. Oh, with your brain. Okay. You know, they used to call, before the days of electronic calculators, they used to call brains calculators. Oh. Right? I didn't know that. Yeah. Have you seen that NASA movie, Hidden Figures? Yeah. What did they call those ladies? They called them calculators. Yeah. Give me some calculators over here. You mean the big computer that's taking up the entire room? No, we only have one of those anyway. That would be singular, not plural. Oh, I'm lost. I'm from the future, okay? In the future, calculators are handheld devices. Okay, with our brains, what do you get when you plug in a 0? Let's try that. Let's just try f of 0. What's 1 over 0? Doesn't exist because it's some type of, which means the y values are some type of infinity. Okay, let's say it's positive infinity. What would sine be doing as it approaches infinity? Oscillating betwixt which two values? 1 and negative 1, 1 and negative 1. Are you ever going to be able to predict as you go further and further out to the right where it's going to stop? If it ever stops, does it ever stop? No. Okay, it keeps going, oscillating. If 1 over x then gives you negative infinity, what's sine doing as it goes out to the left towards negative infinity? Oscillating between negative 1 and 1. So what do you think the limit is as we approach 0? Well, if you say the limit is infinity, you're saying as you go out further and further, it's going to go 1, negative 1, 1, negative 1, 1, negative 1. What the heck? Go up to infinity. Does it ever do that? No. Would it be 0? I'm tired of oscillating. Would it be 1? I'm tired of oscillating. 1. I'm tired of oscillating negative. It's D&E. It's D&E by oscillation. Because when you approach 0, it's approaching infinity. And as sine approaches infinity, it just oscillates forever and ever and ever. Okay? Now think about this so we can generate the graph. Remember the thing that's inside the sine or cosine function affects the period of the graph. And it's kind of the reciprocal here. So what happens to the period or the length of one cycle as x gets really, really big? Like if you plug in a 10, the period is like 1/10. If remember, b was the number of cycles in 2 pi. So when x is 10, you have a tenth. So now you're only seeing a tenth of a cycle between 0 and 2 pi. So in order to see the whole thing, you have to go out 10 times further. So it's stretching it. What if you plug in like 1,000? Now you're only seeing 1,000th of one cycle. So to see the full cycle, you got to go out 1,000 times that way. So as x gets bigger, the period is getting bigger. It's stretching, okay? And what happens now if you plug in a number between 0 and 1, like 1/2? What's 1 over 1/2? 2. So now you're seeing 2 cycles where you saw 1. That's doing what to it? Compressing it. If you plugged in a 1/10, now you're seeing 10 cycles. So here's what's interesting. If you looked at the graph, here's 1, here's -1. It's coming in like this, nice and stretched out. And then once it gets past 1, it starts oscillating faster and faster and faster because the period gets smaller and smaller and smaller, and it oscillates between -1 and 1 constantly faster and faster and faster. I just burned the tip. Woo! Okay? And it does the same thing from the other side, nice and slow, and then it starts oscillating faster and faster because the frequency gets higher, if you want to think about that. Okay? Does it ever reach the y-axis from either side? No, I've been doing this problem for 19 years now. And from the first day I taught it, it has still been moving closer and closer to the y-axis, and it's not reached there yet. We'll tie this up in a bow when you get back from lunch. Have a great lunch. Yes? Moment.